Okay, good morning. We're going to go through some stuff about radiation. So before we go into radiation, just a reminder about the structure of the atom. Inside the nucleus, we have got protons and neutrons. The nucleus is positive, and it's also responsible for 99.999% of the mass of an atom. The electrons are in the outer shells, and they are negative. The electrons have got a very, very small mass, but they have got the same amount of charge as a nucleus. A neutral atom contains equal numbers of protons and electrons. So neutral atoms have no overall electrical charge. All atoms have an element of the same number of protons in the nucleus, and this means that if I was to have carbon, which we see in our periodic table as carbon 612, I can change the mass number of that by increasing the number of neutrons. Well, neutrons have got no charge, and they have the same mass as protons. We call those different types of atoms isotopes. Iso means the same, and tope means place. So carbon 612, carbon 613, and carbon 614 would all be in the same place of the periodic table. If I increase the number of protons, like I did accidentally over there, don't know why I did that, it becomes a new type of atom. So carbon with one extra proton becomes a nitrogen. Nuclei of some atoms are unstable. So this is an unstable atom. We can also call this parent atom. Parent nucleus, pardon me. To become more stable, to give out radiation. So the nucleus decays and it releases some kind of radioactive particle, or in the case of gamma radiation, some energy. It decays to form another nucleus, which is more stable. Now, this can either mean that you have a new type of atom. So if this is carbon 612 and undergoes some kind of a decay, it could turn into a new atom, or it could just release energy and stay the same kind of atom, carbon 612. Activity is the rate at which a source of unstable nuclei decays. It's measured in becquerels. So if I detect, say, 30 of these particles every second, then that is the same as 30 becquerels. The count rate is the number of decays recorded in each second by a detector. Now, this is a Geiger-Müller tube. The way Geiger-Müller tubes work is you have an incomplete circuit here. The outside of the Geiger-Müller tube is positive, and the inside filament you see here is negative, but there is no connection. The only time there will be a connection is when when you have an ionized atom inside. It will be gas, because gas is what makes up the air around us. Now, this is a radioactive rock releasing radiation. That radiation will enter through the Geiger-Müller front. It will interact with a particle. That will become an ionized gas, and it will make a connection between the 2 points, the positive and negative points. This completes a circuit. We get a tick and we get a beep, or a click. Different radioactive isotopes decay at different rates and emit different types of radiation. So what that means is something like carbon can take thousands of years to decay, whereas something like I think lithium-38, it decays in like milliseconds, fractions of a second. There are three different types of radiation that we have to know about: alpha, beta, and gamma radiation. Alpha radiation is the largest. It is made up of 2 protons and 2 neutrons. It is unable to penetrate anything less than paper or 6 to 8 centimeters of air. Beta radiation is much more, has a better ability to penetrate. Beta radiation is able to get through paper, but it's stopped by aluminium. The reason for that is that aluminium is more dense. So more particles than aluminium to stop that beta radiation getting through. Beta radiation can either be made up of an electron or a positron. Gamma radiation is the most penetrating. It is not made up of any particle. It is just made up of electromagnetic waves. So radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. All 3 types of these radiation can cause ionization of other atoms. And all that means is if I have a nucleus with 2 protons and 2 neutrons, and there are 2 electrons orbiting the outside, it is a neutral atom because I've got two negative charges and two positive charges. If I was to release one of those electrons into the environment, then I would only have one electron, but I would still have two positive atoms, meaning that it would be a positive, not positive atoms, positive particles, meaning that you would have a positive nucleus. And this is what makes an ion. It is a charged particle, a charged atom. Gamma rays, beta emission, and alpha emission are all ionizing. If these atoms, if these radiations, if this radiation interacts with living cells, it can cause damage to the cells, which could lead to cancer. So specifically, if the DNA inside our cells is ionized, then we can get cancer. Now, alpha is the most ionizing. The reason for that is it's got plus charge, a charge of +2. Beta negative radiation has got a charge of -1. Beta positive radiation has got a charge of +1, and gamma rays has only got a tiny amount of charge. They're all ionizing, but alpha is the most ionizing. They're all penetrating, but gamma is the most penetrating. In alpha emission, the nucleus loses 2 protons and 2 neutrons. The atomic number will reduce by 2 and atomic mass by 4. So this is the atomic number here, uranium-92. It releases 2 protons and 2 neutrons. The symbol for that is this. Because the nucleus of helium is 2 protons and 2 neutrons, we say that the alpha radiation releases the nucleus of a helium atom. So we give it the symbol He. It could also have a symbol that looks like that. And when this happens, uranium turns into thallium. So the mass number of thallium is 90. The atomic number of thallium is 90, and the mass number is 234. We can see that the atomic number has gone down by 2, and the mass number has gone down by 4. In beta emission, the nucleus loses an electron, which is produced when a neutron turns into a proton. So the mass stays the same, but atomic number of the product increases by 1. What does this mean? It means that inside this carbon atom, there is a neutron. And that neutron is going to turn into a proton and an electron. So we can see that the mass number increases, the atomic number increases by 1. It goes from 6 to 7, making my new atom nitrogen. Mass number stays the same because the mass of a neutron is equal to the mass of a proton. That's a symbol for beta negative radiation. We could also do this with beta positive radiation, carbon 614, and this is when a proton turns into a neutron and a positron. So instead of my mass number increasing by 1, it's going to decrease by 1 because my proton is turned into a neutron and a positron. So my mass number decreases by 1, giving me the element boron. I don't know why I'm doing this. This is the atomic number. The atomic number decreases by 1, keeping the mass number the same. And we have a positron particle released. So a way to remember this, I asked my teacher if I can go to the toilet. And the teacher said, no. And then I said, no pee. That's making me very sad. And then the teacher relented and said, fine, pee now. Which made me very happy. Why are we remembering this? Because this is alpha radiation, this is beta negative radiation, and this is beta positive radiation. 2 protons and 2 neutrons released make alpha radiation. When a neutron, N for neutron, N for no, turns into a P for proton, it releases a negative particle, beta negative radiation. When a proton, P for proton, turns into a neutron and a positive, yay, happy, smiley, positive thing, positron radiation. So PP, no, P makes me negative, P now makes me happy. And then gamma radiation, there's no particles emitted, so there is no change to the nucleus. The atomic mass and the atomic number stay the same. So this is, I believe, tectinium. Tectinium will stay tectinium, but it will release gamma radiation. Okay, so radioactive decay is a random process. So the likelihood of decay taking place is a probability problem. For this reason, the half-life of an isotope is given rather than saying how long it will take to fully decay. If you flip a coin once or twice, you don't know whether or not it's going to be heads or tails. You can't predict it. But if I flipped a coin 1,000 times, I'd be pretty sure that about half the flips would be heads and about half the flips would be tails. So even though flipping a coin is random, we can still make predictions about it. Same thing for half-life. The half-life of a radioactive isotope is the time it takes for the number of nuclei of the isotope in the sample to halve. So if this was an entire block of uranium, over time, it would decay and it would turn into thallium. So my red blocks here are uranium and my gray blocks here are thallium. The amount of time it takes for one half of those nuclei to decay is called the half-life. We can see that in charts. You start off with 100% of uranium. It decays randomly, but predictably. When there's 50% uranium, that's the half-life. It could also be called the time it takes for the count rate for a sample containing the isotope to fall to half its initial level. Say hi, Mr. P.
Hi, Mr. P.
Mr. Patrick's funny. There's a big range of half-lives in radioactive isotopes. You do not have to know them. You do not have to remember these. You may have to work them out and you may be given them to understand. Lithium-38, like I said, good me for remembering. It's about 0.838 seconds. Uranium-235 can take 703 million years to decay. What does this mean? If I have 1 kilogram of uranium-235, after 703 million years, I will have 500 grams of uranium-235 and 500 grams of thallium-235. Short half-life radioactive isotopes often give high doses of radiation. So if I have a kilogram of lithium-8 and I stand beside it, within 0.838 seconds, I will have had a lot of radiation impacting on me. I would have absorbed a lot of radiation. Long half-life isotopes are low-dose hazards, but they're around for a long time. Uranium-238's main fuel, nuclear industry. It is very slow at emitting radiation, and it's actually quite safe. We have a chunk of uranium rock in our safe, and it's pretty much okay to hold it in your hands. But iodine-131, which is made during the whole process, because of course nuclear power requires the atoms to break down through radioactive decay, thereby releasing radiation, so that we can power our turbines and boil our steam. Much more dangerous because they emit radiation at a faster rate. Iodine-131 is also soluble, so they get into the food chain more easily. One of the first things that you have to do if you're at the site of a nuclear accident is take iodine pills so that your body is saturated with iodine. No more iodine can be absorbed by your body, and you avoid getting things like thyroid cancer. If you know the start and the finish count rate and the time taken, you can calculate the half-life. So if the count rate of an isotope is 1008 becquerels, and it falls to a count rate of 126 over a period of 21 days, we can figure out what the half-life is. So we start with 108. We half that to get 405, half that to get 252, half it again to get 126. There are 3 half-lives between the time of the first count and the last count. If there's 21 days of time from here to here, then we can figure out what the half-life is. We just have to divide that 21 days into 3 chunks. So 3 half-lives took 21 days, the half-life is 7 days. You can also use a graph to do it. So we started off with 200 as our count rate. When our count rate went down to 100, we draw an intercept, and we see that the amount of time taken was 1.2 hours. For 50%, the amount of time taken was 2.4 hours. So the half-life, 1.2 hours. Radioactive materials are hazardous to life. Nuclear radiation can ionize, which means the matter remove electrons, substances within the human body. This can change the way cells behave. They can damage DNA or destroy human cells. The effect of ionization on different body parts. Hair can cause hair loss by killing the skin cells underneath your scalp. It can cause burns or lead to skin cancers on your skin. High doses of radiation can cause sterility or mutations in offspring. Have a look at some of the animals coming out of Chernobyl at the moment, and you'll see that they have mutated in some way. Exposure to radioactive iodine can destroy the cells in the thyroid or cause cancers. And if your bone marrow gets destroyed, which is the gooey stuff inside your bones, it can cause leukemia and other blood cancers. Rapidly dividing cells, like cells that produce hair or those in reproductive organs, are most susceptible to ionizing radiation. Now, there are two different things that can happen when you're exposed to radiation. One is irradiation, and that's where an object or person is exposed to radiation. Protection from the radiation means stopping the radiation from reaching. So you can put up a lead screen, you can wear protective equipment. I wear my lab coat when I'm doing the demonstrations in school. But it doesn't actually cause any damage to physical things. Medical dressings are often irradiated, but present no danger to the user. So if I was to irradiate a piece of cloth, then all the nasty, germy, buggy type things on that cloth would be destroyed, my cloth would be sterile, and then I could use it. However, contamination is when a radioactive source is in contact with an object or a person. So if you were to swallow a polonium pill, the radioactive substance is inside you, and the emissions are always present. This subject remains radioactive until the contamination is removed or it decays naturally. So if I was to swallow some lithium-8, say, I don't know, a gram, after 0.838 seconds, there would only be 500 grams left, and then after another 0.838 seconds, it would be 250 grams, and then 125, and so on and so on and so on, until there's so little of it left that it's not producing any more radiation. However, during all that time, the emission is interacting with my body, increasing the chances of ionization. Radioactive materials are hazardous, so precautions can be taken to reduce the risk when using radioactive sources. Wear protective skin and limit the dose and monitor exposure using detector badges. Now here's some questions. They'll be on the screen for about 10 seconds. Now these are some intervention questions. You don't have to get them all right, and they're only here if you excuse me, they're only here if you need them. But they're just a bit more practice on things that people find especially tricky, and half-life is one of those things. So take your time going through them, and if you have any questions, all you have to do is ask. My one piece of advice for you is, if you were going to be doing these questions, these half-life questions, then draw them out, draw those diagrams the way that I was showing you earlier on. So it looks something like this. Oh no, I've got a spinning wheel of death, and I don't know what to do. Okay, am I back? Lovely. Okay, so Mendelevium 257 is a half-life of 5.5 hours. The source contains 36,030. Oh, come on now. I don't know why this is happening. Contains 36,000 Mendelevium. How many would remain after 5.5 hours? So it's a half-life of 5.5 hours. Draw an arrow that represents the half-life, 5.5. After that 5.5 hours, this will be halved, giving me 18,000. After 5.5 hours, 18,000 would remain. So give that a shot just while we're here. Here are the answers. These will be on the screen for 10 seconds. And some more answers. Some more answers. I don't have to say that too loud. Just talking to myself. And again, these are the answers for those intervention questions. And the answers for the half-life questions. And what I'm going to do is I'm going to pop up some decay equations as well. So looking at these equations, you've got to find the missing numbers. So for example, for this one here, actinium-255 releases alpha radiation, helium nucleus, 2 protons, 2 neutrons. So that means that the proton number will have decreased by 2, giving me francium of 87, and the mass number will have decreased by 4, 251. You will have to use your periodic tables inside your planners, and you'll have to use these. These ones aren't actually included in your planners. So if you can't find the atom that you're looking for, the element that you're looking for in your periodic table, have a look at the periodic table above. And here are the answers. All right. Thank you very much for listening, and best of luck.